All right, so this is Electrical 3, Module 1. (26.301-20) load calculation with branch and feeder circuits. All right, Module 1. Like I've said, I don't want to intimidate too many people, but this is the hardest module that I teach out of anything I teach at NIMS. All right, so this is like, I teach all of instrumentation, I teach all of electrical. This chapter is the most difficult to pass, but it's the first module in the book, so I'm on page 1. So there's a lot of math in this, there's a lot to remember. So stick with me. Try to work these math problems out and stuff like that, and ask questions. If something doesn't make sense, ask questions. So on page 1, first module in the book, 26301-20. So the purpose of why we're doing this is to determine the size of branch circuit overcurrent protection in conductors. So what's an overcurrent protective device? What's an example of one? The hardware component that will protect a circuit from being overloaded. Fuse. Fuse is one. What's the other most common one? Fuse or breaker. A breaker. Good. So anytime you see overcurrent protected device, for the most part, it's going to be a fuse or a breaker. So going through some of the trade terms in this section. You need to know what these are. Ampacity we've talked about, but ampacity is the maximum current that something can handle. So that would be its ampacity. Branch circuit you've heard, but it's the circuit conductors between the final overcurrent device. Again, what's the final overcurrent device more than likely? A fuse or a breaker. Protecting the circuit, so that's from your breaker to wherever your circuit is. Say it's wall outlets or something like that. That's the branch circuit. Anybody remember what another name for branch circuit is? What they're going to call what residential electricians will call a branch circuit. The conductors that connect from the panel to the circuit, it's called a home run. Ever heard that term before? So home run is like going back home like that, or going back to the source. That's a home run. Continuous load. None of these, I don't have any of these highlighted, but these are going to be important. We're going to use continuous load a lot. You're going to be looking for continuous load in these questions because it will completely change the answer. The continuous load is a load where maximum current is expected to continue for 3 hours or more. So this would be like a lighting outside of a business. Like you turn your lights on for your business at night. Everybody expects that those lights are going to stay on for 3 hours or more. Stuff like that. Everybody should know what an outlet is, receptacle, overcurrent. Should probably, if you don't know what any of the rest of those are, please read through those. They go through most of those trade terms on page 1, so I would recommend reading through that, especially that blue note on page 1. It talks about continuous loads. Like that's a good example of how to size continuous loads. But I don't have any highlights on this first page, but yeah, the green note is a good thing to highlight if you're not understanding what continuous loads are. Page 2. My first highlight on page 2 is it's like the third green highlight where you see NEC table 220.12. That through the end of the paragraph is highlighted. NEC table 220.12 gives general lighting loads listed for various non-dwelling occupancies. These general lighting loads are expressed as a unit load per square foot in volt amperes. Volt amps. Anybody know what a volt ampere is equivalent to? So if I had something rated, if I had a toaster, it was rated for 100 watts. We'll say 50 watts. 50, not 50 watts, sorry. Volt amperes. Say it ran at 2 amps. What voltage is the toaster going to run at? What's the voltage in your house for every plug for the most part? 120, right? 120. So this is my amps, and this is my volts, right? So volt ampere, if I multiply these together, I get 240 volt amps. Volt amps is also equal to a watt. So everybody, y'all have used generators and stuff like that before at your house, power goes out, or at least heard of people that have used those. A pretty common size generator, like just going and buying one from Home Depot, is about 6,500 watts. So this is all like load calculations. This is all so that like if my toaster uses 240 watts, and I'd have to go in here and go 240 and then do your calculations to see what that generator would actually run. So that's how you size like what size generator you need for your house. Anybody have a whole house generator? We have one of those. So those are even bigger, like usually 6,500 watts. That's your like little roll around generator or something like that. But if somebody puts in like a whole house generator, that's going to be more like it would be more like 22,000 watts. Whatever, 22,000 versus 6,500. So you can see like it's 3 times as big, and that's so that it can run like your air conditioning and stuff like that. The next highlight is the next paragraph, first sentence. For example, the unit lighting load. Unit lighting load for a school is 3 volt amps per square foot. A retail location is 1.9 volt amps per square foot, and a warehouse is 1.2 volt amps per square foot. What that means is if I had a school building, like this building that we're in right now is probably around 150,000 square feet. So if I had 150,000 feet squared, what's my number for school buildings? Three volt amps per square foot. So I would multiply this by 3 and get 450,000 watts or volt amps. Right? So that would be my first step in like saying I need this much power at this building. Right? It's just a general, whenever they say general lighting load, they don't mean like what's going to turn on the specific lights. Lighting load means like everything. General lighting load is like to light up this building, how much is it going to take? All right. So step 1 would be find your, everybody flip to 220.12 in their NEC book. There's more in this cabinet right here if you need. And you'll need to take these home and make sure you bring them back because we're not going to make it all the way through this today. But yeah, 220.12. So that is on, if you can't find it, it's on page 70-75. Remember, I told y'all can mark these pages and stuff like that. If you want to mark them with notepads, feel free. I would mark one of these if I was y'all. But if I look at that list, I can see like automotive facility, convention center, courthouse. All these are different numbers that somebody came up, some engineer did the math a while back and said like these buildings are going to need this much power and stuff like that. So you can see where like a manufacturing facility is gonna need 2.2 volt amps per square foot. Or down at the bottom, a school or university is gonna need 3, whereas like a lower number one would be like 0.3. Parking garage. Parking garage, what do you have in a parking garage? Lights, right? Pretty much just lights and maybe a few plugs and stuff like that, maybe a fan, but it's not gonna take a lot of electricity. Does this make sense? All right. So branch circuit ratings, 110 on page 2. Branch circuit ratings. So you're multiplying the rating or setting of the overcurrent device by the voltage. So that first example they give, the maximum load that may be supplied by a 20 amp 2-wire 120 volt circuit is 20 amps times 120, which you get 2400 volt amps or 2400 watts. So a 20 amp breaker can only supply 2400 watts, right? So if I had my 2 amp toaster right there, how many toasters could I put on that circuit? 10. So if I put 10 on there, so multiply by 10, that gives me 2400. If I see that, I can put 10 toasters on that outlet before it would either fry the wires or hopefully trip the breakers. Breakers, just so y'all know, breakers are not meant to save lives. Like they're not meant to be for human safety and stuff like that. Breakers are made in size so that your wires don't melt inside your walls, right? Because if I just put a gigantic breaker on smaller 12 gauge wires, that breaker's not going to trip when those wires are sitting there melting its coating off of the wall. So that's why you have to size them together. You don't size them separately. You size them. You have to see how much current you need, and then you put the breaker in there, and then based on that breaker, you size your wire because you want everything to go together. Down all the way at the bottom left, online test question, they did the 3-phase calculation. So that all the way in the bottom left, right above that note, all that's highlighted. The maximum load that can be supplied by a 20 amp, 208 volt 3-phase circuit is determined by multiplying the 20 amps by 208 volts by the square root of 3. So if it says 3-phase, you're multiplying by the square root of 3. All right. The next in the top right, that paragraph in the top right, and all of that note, I have 5 questions that come out of that. So I just highlighted that whole entire paragraph along with that green note in the top right of page 2. Branch circuits may supply non-continuous loads, continuous loads, or a combination of 2 per NEC section 21020A. The branch circuit rating shall not be less than the non-continuous load plus 125% of the continuous load. A continuous load is defined by NEC Article 100 as a load whose maximum current is expected to continue for 3 hours or more. 3 hours or more. Please don't miss that. Like, they're going to ask questions about continuous loads. 3 hours or more is considered a continuous load. Continuous loads are calculated at 125% of the maximum current rating of the load. The note is a little bit confusing, but I'm going to read through it and try to talk through it. The reciprocal of 125% is 1 over 1.25, which is equivalent to 80% of the rating of the overcurrent device. I.e., you will get the same result when you divide by 1.25 as when you multiply by 0.8. The reciprocal can be used to calculate the maximum load that could be connected based on the circuit rating. So what this means is if I have a continuous load, say I had lights outside of the business or something like that, and say they ran at 5 amps, right? So if it runs at 5 amps, if they run at 5 amps, and it's considered a continuous load, what do I have to multiply by? That last sentence before the note.
0.8.
Not 0.8. It's 0.8 if you're determining the breaker. But if you're determining the actual load size, you're multiplying by 125%. That make sense? So I'm taking this 5 amps times 125%, which is 1.25. And I'm saying, pretty much saying that 1.25 times 5 is going to be 6.25. So I have a 5 amp load that'll run for 3 hours. I have to pretty much pretend that it's a 6.25 amp load whenever I'm doing all my calculations because it runs for so long. Does that make sense why they're doing that? So if you have something that runs for 3 hours or more, you have to multiply that load times 125% to get what you're sizing that load at. Okay? Second to last paragraph on the page, right above example 1, the bottom right of page 2, that whole paragraph is highlighted. For 15, and this is an online test question, for 15 and 20 amp branch circuits, NEC Article 210.23A2 allows fastened in place utilization equipment to be connected to the same circuit with lighting loads or lighting units, cord and plug utilization equipment not fastened in place, or both. Under this condition, the fastened in place utilization equipment cannot exceed 50% of the branch ampere rating. The last sentence is what you want to key in on. If you have fastened in place utilization equipment, it can't be more than 50% of your entire load. So they go through, like page 3, they're going through all the problems to figure out what the circuit load is. Most of the time, I'm not going to ask y'all to read entire chapters and go through examples, but this is to read through these and actually go through the examples and even do them, write them out in your own handwriting, side by side with other examples. That is the most beneficial for getting to pass this test. Not going to be like, this is not like a trade term test. This is going to be a lot of math and a lot of knowing when to use certain percentages and calculations and stuff like that. So I highly, highly recommend going through this chapter and getting some of those percentage or doing some of these example problems alongside them. I don't have anything highlighted on page 3, but moving into rating factors on page 4. Page 4. Page 4, right after the bullet points on page 4, that big paragraph that ends the section, I've got the sentence, like the 4th sentence highlighted, I think. If the number of current carrying conductors in the conduit or cable exceeds 3, the ampacity of the conductors must be derated using NEC Article 310.15C1. So if there's more than 3 conductors in that conduit, you have to derate them. We're on page 4, the first module. So if you have more than 3 conductors, you have to derate those conductors. One, 2, 1, temperature derating. First sentence is highlighted. NEC Article 110.14c states that the lowest temperature rating of any component in the circuit breaker, fuse, receptacle, conductors must be used to determine the ampacity of the branch circuit conductor. So whatever the lowest temperature rating is, it's kind of like the weakest link. Everything's determined by the weakest link. whatever has the lowest temperature rating, that's what you have to use for the entire thing. Again, they go through temperature derating example problems. I highly, highly recommend you guys go through and do that, right? Did they talk to you all about this being a hybrid class at all whenever you signed up? So that was kind of my question for, usually this class is taught for 3 hours twice a week at night. But this day class is listed as a hybrid class. So that's why I only get y'all for twice a week at 4 hours. But technically, like they should have told y'all like part of this class will be done at the house. Because I can't cram this stuff in here. So whenever like I'm asking y'all to do this work and stuff at home, like that's part of this class because technically we don't get all the hours that we're supposed to in class. That's why this is a hybrid. Y'all are supposed to work on this at home. So there's going to be quite a bit of stuff to do that I hope you guys do in between now and Thursday. But that's going through these examples and understanding when you're taking what percentage of something to derate it. Like that's kind of what responsibility I'm putting on you guys to do after today's class. Page 5, voltage drop derating for single phase circuits. The entire first paragraph is highlighted. NEC section 210.19a informal note number 3 states that reasonable efficiency will be provided by branch circuits in which the voltage drop for the branch circuit conductors does not exceed 3%, and the farthest outlet 5% for the combination of the feeder and branch circuit distance to the farthest outlet. We did voltage drop calculations already, right? We did that, both of these voltage drop equations. So this chapter, you're going to be using these a little bit more. So highlight those. You got 2 formulas. So there are 2 formulas used to calculate voltage drop for single phase circuits. Highlight that one at the bottom left. Voltage drop is equal to 2 times L times R times I over 1,000. And then the one in the top right, voltage drop is equal to 2 times L times K times I over your circular nose or your area. We've done problems like that before, so you guys will be doing the same thing. Usually it's kind of backwards. I've done this chapter first, and then the other one. But this one we've kind of done the other one and then this. So this is where you'll need that chapter 9, table 8, all the way to the back of your book, looking up those circular mills for different sizes of wire. Flipping over to page 6 and 7. So this is where they're doing their sizing out copper conductors. On page 7, I've got example 3 highlighted, and you're going to have a couple questions come out of that example. So example 3 on page 7, which size THHN copper conductors would be recommended for 240 volt single phase 3-wire branch circuit with multiple power outlets consisting of 3 fixed 240 volt 30 amp loads at 60 feet, 30 amps at 80 feet, and 20 amps at 100 feet. So I'm just going to run through this example, like what I'm asking you guys to do. I'm going to do with this example. So that's the question. Solution. First thing you want to do is determine the length center of the circuit by first multiplying the outlet loads by their distance from the circuit source. So outlet 1, if we look up at the top, the first one is 30 amps at 60 feet. All right, so outlet 1 is 60 feet times 30 amps equals 1,800. Outlet 2 is 80 feet times 30 amps, which is 2,400. And outlet 3 is 100 feet at 20 amps, which is 2,000. You add all those together, 1,800 plus 2,400 plus 2,000 gets you 6,200. And then you divide by the sum of the loads. So 6,200 divided by 30 plus 30 plus 20, which is 80. And then you get 77.5 for the load center. So you have a couple of questions based on that, and then I'm gonna do a question up on the board. Everybody know what that means? Does anybody know what that means? I wrote that next to it. What'd you guess? Phase. Single phase or three phase. This is a different sign for phase. That means 240 volts, single phase. Everybody knows what that means, right? All right. So that question right there. What size copper conductor would be required for a 240 volt single phase circuit supplying a non-continuous load of 27.5 amps at a distance of 145 and a maximum voltage drop of 3%? One second. All right, so if we know that we don't want to exceed a voltage drop of 3%, everybody see that equation all the way in the bottom right of page 6? Let me try to explain this. So our original equation is voltage drop is 2 times L times K times I over circular mills. Everybody's good with that, right? Now moving stuff around. If I know my voltage drop needed to stay at 3%, I can switch stuff around, right? If I wanted circular mills to go over here, how do I get it over there? I remember, y'all should know this, high school math. Multiplying it. So I would multiply by circular mills. That would cancel out, multiply by circular mills. So voltage times that times circular mills is equal to 2 times L times K times I. And if I'm looking for my circular mills and I want to get voltage drop over there, how do I do that? Divide it. So voltage drop, that cancels out. Put voltage and distance over here. So pretty much I can have that equation, right? If I want my voltage drop, and that's what they have in the bottom right of page 6. So if I want to know my size, and I know my drop has to be less than what percentage? 3%. What's 3% written as a decimal? Or let me just take this. Let me take this equation and move it back to the other one. So circular mills is equal to 2 times L times K times I over the voltage times my voltage drop, right? So writing in my word bank over here, just going through my question, what size copper conductor would be required for a 200 volt single phase circuit supplying non-continuous load, 27.5 amps? So what's the first piece of information that we're given? Nope. Even before that. If I write out all my unknowns over here, I have L, K, I, voltage, your drop. Your drop is what? 3% written as a fraction is what? 0.03. Everybody good with that? All right. So for these other ones, what's my first one that it tells me?
It's copper.
It's copper, right? Y'all remember K has 2 different variants. One's for copper. What's the other one? What's the other? Aluminum. Y'all, anybody remember the numbers? 12.9 for what? Copper. 12.9. What was aluminum? 21.2, I think. So aluminum. So the first thing I know is, and then what variable is that? K. So 12.9 is my first one because I have copper conductors. What's my next thing I can put in my bank? Before that, the volts. It's right there, 240 volts. Single phase. So that means that I am not doing what?
Multiplying.
Multiplying by what? If I have 3 phase, what do I multiply by? Square root of 3, right? So this tells me that I don't have to do that. And then this tells me that I don't have to what? It's not going to run for more than 3 hours or more. So I don't have to multiply this by 125%. So then my next variable that it gives me is what? What variable is that? I. 27.5 amps. What's my next one? My distance or my length at 145 feet. And then the maximum voltage drop for 3%, that's the one that I gave you right there. All right. So now we go plug these in. So circular mills are equal to 2 times L. So 2, my L is 145, 145. My K is 12.9. My I is 27.5. My voltage is 240. And my drop is 0.303. This is 3%. Okay. So now I'm finding what is CM? Circular mills, which is the area of the size of my wire. So this is how big my wire is. So everybody put this math in your calculator, your phone, or however you want to do it. Like I've said, I highly recommend a calculator like this for these tests. I think they sell them in the bookstore up there, but they also sell them at Walmart for like $10. What'd y'all get?
12.85.
I get something different? Should be way off.
I got 14,288.5417.
You got 0.5 what?
417.
Close enough. I got 0.54, which really doesn't matter. So if you didn't get that, make sure. Yeah, I'm not sure. Make sure you're doing this math right here. You got your decimal point in the right spot. But yeah, this should be the answer that you got. So again, what is that? That is a size of wire. So where do we go to look for size of wire? Chapter 9, Table 8. So everybody turn to Chapter 9, Table 8. So Chapter 9, Table 8. In your NEC book, which should be on page 70-705. What size wire would be big enough for that calculation?
Three gauge.
What's your circular mills of 3 gauge?
16,000, no, 167,800.
Where are you looking? So you're looking at your circular mills? So for 3 gauge. Is that what you're looking at? You're looking here.
No, I'm looking at
So that's 3R.
3
This is 3 gauge.
Okay, 3
All right. So what you're looking for is the size that is big enough, but not any bigger than that. If that makes sense. Because you don't want to buy extra big wire, because this could be thousands of feet of wire. So you want the size that's just big enough. So what size wire has over that amount of area, not 3
Oh, no.
Because that's 167,000.
Right.
We're looking
They
for-
did number wrong.
We're looking for 14,000.
8, yeah.
8. Why does 8 work?
16.
16,510. Is that bigger than that?
Yeah.
Yep. If you go down to 10 gauge, remember 10 gauge is smaller. What's the size of 10 gauge?
10,000.
10,380. Is that big enough? No. So you have to use 10 gauge or 8 gauge wire. There's mud. If I was you, I'd take a picture of that problem, or if you haven't written it down, that's gonna be I would know how to do that problem, for sure. Going back to page 7. Did you get this? You wanted it? Page 7, going to 1, 2, 3. That first paragraph, and then the 2 formulas are highlighted. The voltage drop for a balanced 3-phase circuits with negligible resistance and power factor of 1 can be calculated using 2 formulas above by substituting square root of 3 or 1.732 for the value of 2 in the formula. So this is for 3-phase circuits. Instead of using that 2 times, you're using the square root of 3 times. So all you're doing there is if you saw this question right here, and it said instead of this, it said 3-phase, you would have to do this voltage drop equation. Instead of having 2, you would have the square root of 3. That's it. You just have to watch. You just have to watch what you're looking at. I'm not going to go too much into those because it's the same thing, just one number is different. Page 8, 130, branch, circuit, and capacity. 130. First sentence is highlighted. The branch, circuit, and capacity for single-phase circuits calculated by dividing volt ampere by the current circuit voltage. I have example 2 highlighted as an online test question. So I'm going to run through that question with you. What is the ampacity of a 3-phase electronic water heater with a nameplate rating of 20 kilowatts and 208 volts? All right. So it says the first step is to multiply 20 kilowatts by 1,000. Why am I multiplying 20 kilowatts by 1,000?
That's the rating of the.
It's the rating of the water heater, but for my math, my units have to be in watts, right? And a kilowatt is 1,000 watts. So if I say that if they're saying that I have a 20 kilowatt water heater, I have to have that in watts. So just being sure 20 kW is equal to 20,000 watts. Everybody good with that? The easy stuff. That's the first thing they're doing. And then divide the result by the voltage times square root of 3. All right? So what did I say? A watt is equal to what? A kilowatt is equal to 1,000 watts. But what is a watt as far as terms go equal to? The amperage times what? The volts. So a watt is equal to volt amps. I'm going to push that more and more and more and more. I like saying volt amps because that makes sense. So if I have 20,000 watts, that means I have 20,000 what? Volt amps. okay? And if they're wanting to know what the ampacity is, so if I'm wanting to know what my ampacity is, what do I have to divide out of this?
The volts.
The voltage, right? So what's my voltage in the problem?
208
208 volts, but it is also what?
times. Wait, 3 phases.
It's 3 phase. So what do I have to multiply my voltage by?
1.7.
Square root of 3 times square root of 3. So all they're saying with that 1.7, all they're saying is the square root of 3 is equal to 1.7, whatever they say it is. What? 1.732. It's hard for me to remember that number, but I can remember 3 phase square root of 3. All they're saying is like you can put square root of 3 in your calculator and it's going to come up 1.732. That's all they're saying for that. But whenever you're having to memorize this stuff, this is easier. So I can say divide out by my voltage, right? Because this is my volts. Essentially what I'm doing is getting rid of my voltage by dividing it out. So what's 208 times the square root of 3? Put that in your calculator. I want to make sure everybody, like, I know it's written on your in the example and stuff like that, but make sure you know how to do square roots and stuff in your phone. I think some of them you have to flip sideways too. I don't see it, ask your neighbor. But make sure that you know how to do that. Just so y'all know, this test, you can't use your phone. That's another reason why I push getting one of these little simple calculators like this. Like I have 2 of them that I'll let people use, but I have 2 of them. That's it. Y'all have one of these big, the TIA-3 calculator or whatever y'all use now in high school, are very good for this because it shows everything you're doing. But I highly recommend not doing these problems with your phone because you're not going to be able to use it on your test. Okay. So what's 208 divided by square or times the square root of 3?
360.25.
And then 20,000 divided by that. 55.52. And what's my units that's left? Amps. You got 3 questions on page 9. I want you guys to work through those. Work through them on your page. If you have questions, holler at me. But I wanted everybody to work through those 3 problems for the next few minutes. hint for number two, you're finding, you need to find, you're using the equation with the R in it, you find the resistance in chapter 9, table 8. Instead of 2 times L times K times I, usually 2 times L times R times I over 1,000. All right, let's run through these. So number one might have been a little confusing, or might be a little confusing. So the question is, what is the maximum continuous load that may be connected to a 20 amp, 120 volt fuse? So before we get going, so I've got the fuse, right? This is 20 amp, that's 120 volt. Fuse connected to some type of load. So they're asking, what can I connect to that load? And then what's the key thing that it says? Continuous. So the answers that they give you are 10, 16, 20, and 25. So 10 amps, 16 amps, 20 amps, 25 amps. Just looking at this, what do I know that I can't connect to a 20 amp fuse? 25. I can't connect a 25 amp load to a 20 amp fuse, right? I know that's where some people got messed up because they saw continuous and you multiply by what? Normally you would multiply by 1.25 and get 25 amps, right? Probably some of y'all got that answer. So just thinking, so what you did before was you were sizing this, or you were sizing this with knowing this. Does that make sense? So before you had something that was like 10 amps, that was continuous load. So you would do 10 times 125%, you would get a 12.5 amp load, right? So that's what multiply it by 125% to do this, to see what this should be. Does that make sense? But now they're saying I have a breaker or I have a fuse. What's the maximum amount that I can put on that for a continuous load? So now what do I multiply by? Instead of multiplying by 1.25, whenever you're going, so if I had, say I had this is my fuse right here, and it's unknown, and then I had a load that was a continuous load of 10 amps, and then we just did that, we multiplied this by 125%, and then you get 12.5. So then you would have to get a break or a fuse that would be big enough for that. What's a standard size? Just guessing. Just give me your best guess. What's a standard size fuse that would accommodate 12.5 amps? 15 amp fuse, right? So if I don't know my fuse or breaker, that's where I have to take my load times 125%. But if I know my load, or if I know what size I have for my fuse, I have to derate what I can connect to it because it's a continuous duty load. So what is my multiplier when doing it that way?
You're gonna divide 20 by 1.25.
True. Is that right?
That's what I did.
20 by 1.25.
Because instead of multiplying, you divide.
Yes. So if you go, just humor me for a second. I know this is longer, but going back to page 1. Not page 1. Going to page 2. This is where y'all highlighted that blue highlight or the green highlight note on the right. So yes, where you can divide, you can take your 20 amps and divide by 125%. What's 125%?
16.
What's 125% as a decimal?
1.25.
1.25, right? And what does that give me?
16.
16. All right, just to make it even more confusing, I can also take 20 times what? 0.8 and get 16. I know that's different thing. Like if you want to keep it, I'm dividing by 1.25 if I don't know my load, and multiplying by 1.25 if I know my fuse and not my load. If you want to do it that way, you can, or you can do times 0.8 up here. Does it make sense to everybody how this problem right here can't be 25 amps? I can't have 25 amps on a 20 amp fuse. Everybody's good with that? So I'm just trying to tell y'all to get your best possible shot at getting the correct answer. So number one is B, 16 amps. 20 times 0.8 is equal to 16, or 20 divided by 1.25 is 16. However you want to do that. Number two, the voltage drop for a 208 volt. What does that one mean?
One phase.
Not one on. Single phase. So don't get those confused. That is one phase. With a circuit load of 28 amps using number 8 stranded copper conductors at a circuit length of 160 feet. So the first thing I'm going to do is I'm going to write down my letters and get a bank of data essentially. So what's the first thing that it gives me?
The voltage.
The voltage, which is what?
208.
Volts. What else do I know about that voltage?
It has a load of 28.
Not, nope.
Single phase.
It is single phase. So that's important to know, because sometimes you'll have three phase, but it's good to know whenever you're writing this out, like make sure you know, because 208 volts, that's a very, very, very common three phase voltage. Okay, so usually, not getting into that, never mind. Just denote what phase it is. What's the next thing it gives me?
The amps.
The amps, which is what letter? I, and it gives me 28 amps. What's the next bit of information it gives me?
That's copper.
It's copper. So it's so what would that give me?
K equals 12.
So we also know it's copper. And then it's saying that you're using number 8, right?
Yeah.
So number 8 wire. And then what's the last thing it gives me? 160 feet. So what are my two equations for voltage drop? Okay, so we're gonna do it both ways. I said to use the R1, but we could do it both ways. All right, so which one y'all want to do first? This is probably the one we've used the most, isn't it? Let's do this bottom one first, all right? So 2, what's my length?
160.
What's my K?
12.9.
What's my I?
28.
28. And then what information and then do I have my circular mills? No, but can I find them?
Yeah.
Why can I find them?
You know,
Chapter 9, Table 8, and it tells us what size wire we go. So flipping into Chapter 9, Table 8 on 70-705, and we go down to number 8 size wire. And what's our circular mills? Nope, number 8 wire.
16,510.
Does everybody see that? Chapter 9, Table 8, circular mills is 16,510. 16,510. So 16,5, I know I'm not good at that. All right, plug that in your calculators and what do you get?
That's 7.
That's what I got. I got 7. I go with that. All right, doing my other voltage drop equation right here. I know I'm not the neatest. I'm going to say this is separate. So we're going to use that one. We're going to kind of go over here. So 2 with my length, 160 times R. Do I have R? Nope. Can I find R?
Yeah.
Where?
Table 8, chapter
Chapter 9, Table 8. So what size is my wire?
8.
8. So I go over, everybody see 8 in that table? And then I go over to everybody look up closer to the top and everybody see copper? And then what are we using, kilometers or feet? Feet. And then if it's not noted, do you do uncoded or coded?
Uncoded.
Uncoded. Unless it's marked, you do uncoded. So we are in the copper, uncoded, ohms per kilofoot column. 0.778. Does everybody see that? It is 0.778 ohms per 1,000 feet. Times 28 over what? 1,000. Everybody put that in the calculators. Pretty much the same, right? There's going to be a little bit of rounding stuff. I think and they put their answers close together, but either answer should be D. Does everybody see that? So you can use either one. Honestly, I like this equation better, but there are going to be times where it doesn't give you what that can't be true. I'm not sure when, because it has to give you the type of wire in order to get K. I don't know. Just know that you have both of them. Whatever one's easier for you. I like the idea of doing the bank first. 2 is D. Number 3, the ampacity of 120 volt single phase load rated at 800 volt amps is 6.67 amps. So all I'm doing is taking my 800 volt amps, and what does it want me to know? It wants me to know the amperage. So what do I have to divide out of volt amps to just have the amperage? The voltage. So what's my voltage of this? 120 volts. My voltage cancels out, and that gives me 6.67 amps. Everybody good with these three questions? I'm just going to keep going. Try to get through 2 sections today. All right, back to PowerPoints. Section 2, remember what I said, lighting loads does not mean your power for your lights. It's the entire system that means lighting loads. You know what appliance is, you're gonna have appliance braid circuits. You're gonna need to know what demand factors are. These are all trade terms that are there on page 10. But most of what I'm gonna be worried about is doing this math for this stuff. So really on the right-hand side of the page, I'm gonna have 3 questions come out of that paragraph that's in the top right all the way through example 1. So branch circuit loads for incandescent lighting, this is actually lighting, are determined by adding the total incandescent load for a purely resistive load, such as incandescent lighting, which is watts or volt amps, and dividing the total by the circuit voltage. For example, 3 500-watt quartz lamps are connected to a 120-volt circuit would be calculated as follows. You have 3 lamps times 500 volt amps or watts apiece. That's 1,500 volt amps. 1,500 volt amps divided by the voltage is going to be 12.5 amps. So that's your circuit load. Next paragraph, I've got the first couple of sentences highlighted. Branch circuit loads for electronic discharge and LED lighting. So lighting units having ballast transformers, auto transformers, or LED drivers are determined by multiplying the number of fixture times the ampacity rating of the ballasts, assuming all the ballasts are identical. All that means is it's going to say you might have 3 lamps and each LED driver is going to take half an amp. You multiply 3 times whatever your amperage is. Going down to example 1. Incandescent lighting using 150 watt medium base lamp is required for temporary lighting on a construction site. This lighting will remain on all day and all night. So whenever you hear that the lighting will remain all day and all night, what should that trigger in your head? Continuous load. Very, very good. Like whenever I'm doing these problems, whenever I had to go back and try to I had to learn how to teach this stuff because I didn't do a lot of load applications and stuff I was more like I did troubleshooting and stuff like that. I was never doing the load calculations for buildings and stuff like that. It wasn't my background. So whenever I was learning stuff like this, whenever I was doing my bank of questions, like whenever I saw something like that, I would underline it, make sure that I had that because that is important. If you miss that, multiplying by 0.8 or multiplying by 125%, it ruins your answer. Like it ruins the whole thing. And like everybody knows, these are multiple choice. They don't care if you got every single part of the question right and then forgot to multiply by your continuous load, and they're going to give you both answers. All right. So make sure you'll hit whenever you see that this load is going to be used for 3 hours or more. But because the lighting will remain on for longer than 3 hours, this is a continuous load. For continuous duty, find 125% of 150 watts for volt amperes by multiplying by 1.25 times the following. So all they did is 125% times 150 volt amps is 187.5 volt amps, and then what are they asking for? How many 150 amp can be connected to 20? Okay, so they're saying each lamp takes 187.5 volt amps. A 20 amp circuit can have 2,400 volt amps. 2,400 divided by 187.5, you can have 12.8 lamps. So I can have 12 lamps in that circuit, a 20 amp circuit. All right. Receptacle loads 220, page 11. All the way, first paragraph, all the way through where you see 125% is highlighted. When the exact volt ampere rating of a load, this is in 220 on page 11, that is to be cord and plug connected. The receptacle outlet is not known. A volt ampere rating of not less than 180 volts per outlet is used. Key in on that. If you don't know, each plug is going to be rated for 180 volt amps or 180 watts. For non-continuous receptacle loads, the total non-continuous load is calculated 100%. For continuous loads, the total continuous load is calculated 125%. Same thing, but different than what we've gone over. The example that's down at the bottom of page 11, that you'll need to know that. So I'm going to run through that and just work the math on the board as we're running through it, even though I know they've worked it. So example at the bottom right of page 11. Per NEC section 220.14i, each receptacle is assigned a value of 180. The capacity of a 15 amp, 120 volt circuit is 1800 volt amps. So, just going back to it, our wattage or volt ampere capacity of a 20 amp breaker is what? How do we find that? What's our voltage that we pretty much use for 20 amp breakers? 120. 20 times 120 volts gives me how many volt amps? 2,400 volt amps or watts, right? If I have a 15 amp breaker, what's my voltage? 120 volts. What is 15 times 120? 1,800. So this is how much I can put on a 20 amp breaker. This is how much I can put on a 15 amp breaker. So their question is, how many plugs, what are my plugs rated at? Non-continuous plug is 180 volt amps. It's going to go into this on the next page. But how much, so if I had a continuous duty plug, how much is that going to take up? So what do I have to multiply 180 by if it's continuous? 125. So continuous is 180 times 125%, which gives me what? Somebody do that in their calculator. 180 times 1.25. 225 volt amps. So a continuous duty plug, something that's going to be 3 hours or more, I have to say that it's 225 volt amps. Something that's not continuous, I can say it's 180. So with a 15 amp breaker or fuse, I have 1,800 volt amps available to me. How many non-continuous plugs can I put on that? 10 non-continuous. How many continuous duty plugs can I put on a 15 amp breaker? How would I find that? What is that? 8? Is it directly 8?
Yeah.
Okay, so that's 8 continuous plugs. Right? If I had a 20 amp breaker, how many non-continuous plugs can I put on a 20 amp breaker?
13.3.
What's the math you got to get there?
2,400 divided by 180.
And that gives me what?
13.3.
So how many plugs is that?
13.
13. Can't have 0.3 of plug, right? So for this is a 20 amp circuit. I'm gonna have 13 non-continuous plugs or outlets. How many continuous duty outlets can I have? Take 2,400, divide by what? 225, 10.6. So how many plugs is that? 10 continuous. That making sense? All right, I'm on page 12 and 13, small appliance loads 230. Entire first paragraph minus the last sentence is highlighted in 230. NEC sections 210, 11C1, and 210-52B1 require at least two 20-amp small appliance branch circuits to be installed to supply receptacles installed in the kitchen, pantry, breakfast room, and dining room. NEC section 220-52A requires that the feeder load be computed at 1,500 volt amps for each required small appliance branch circuit. So back when y'all had electrical 1 and 2, how many circuits do I need for each kitchen? 2. You have to have 2 small appliance branch circuits for each kitchen inside of a house. So if I had 3 kitchens, how many dedicated circuits do I need for 3 kitchens inside a house? 6. All right. I only have 1 kitchen in my house, so I only need 2. Usually how this works is if you think about it in your house, usually you have a sink, and then a lot of times you'll have a plug here and a plug here. What else has to be true about plugs on your countertops? I remember GFCI protected, which means that like wetness and stuff has to be GFCI protected. Usually, not always, but a lot of times in houses, they'll have the sink is kind of centrally located somewhere kind of in the kitchen, and you'll have a plug right here on your sink, and you'll have a plug right here on your sink. A lot of times, those are your GFCI plugs. Those are your 2 separate circuits. This one feeds that way, and this one feeds that way, because everything connected to the backside of GFCI is what? It's GFCI protected. You don't have to do GFCI plug, GFCI plug, GFCI plug. Don't do that. You've done it. It's a mistake. Stuff trips. But anything connected on the backside of GFCI plug is GFCI protected. So that's how you have 2 circuits. Go home and look at your plugs and see if that's kind of what you have. But you should have two small appliance branch circuits for each kitchen. And they have to be, what does that highlight say they have to be computed at?
1,500
1,500 volt amps a piece. All right, so I've got that, the example on the right-hand side of page 12 highlighted. For example, what's the total feeder load for 2 small appliance branch circuits rated at 20 amps, 120 volts? To determine this, you multiply the number of small appliance branch circuits by 1,500 to determine the load as follows. 2 times 1,500 is 3,000. You're going to have at least 2 test questions come out of that one highlight. You need to make sure that you're multiplying your branch circuits by 1,500. Laundry circuit loads 240. First paragraph is highlighted. NEC sections 210.11C1, 210.11C2, and 210.52F require the installation of at least 1 receptacle to supply the laundry equipment. Requires that the feeder be computed at 1,500 volt amps for each laundry circuit. So your kitchen has to be computed at what? 1,500. Your laundry has to be computed at what? 1,500. Same thing. Kind of keep that in your head. Next paragraph, first sentence is highlighted. As specified in NEC section 220.54, the load for a household electric dryer must be calculated at either 5,000 volt amps or the nameplate rating of the dryer, whichever is larger. Most of the time, all your dryers are going to be under 5,000 watts or 5,000 volt amps. But say somebody, and usually, like whenever you're an electrician installing this stuff, you're putting in the dryer plug. Like unless something is specified, hey, we're gonna put in this gigantic dryer and it runs on 10,000 watts, you're gonna have to put a specialty circuit in for that, right? Most of the time when they're sizing out houses and stuff, they're saying their dryer's gonna be less than 5,000 and then size it for that. 250, cooking appliance loads. First paragraph, entire first paragraph is highlighted. Loads for ranges, wall-mounted ovens, counter-mounted cooking units, and other household cooking appliances are calculated using demand factors listed in 22055 and the notes alongside of that. The most important single piece of information required to size circuit for residential cooking equipment is the nameplate rating of the equipment. Although 22055 lists loads in kW, 22055 states that kVA shall be considered equivalent to kW for loads calculated using table 220.55. Everybody flip to table 220.55 in their code book, 220.55. Should be on page 70-78. Out to the side of that highlight you just highlighted, right? I wrote in 220.56 commercial kitchen demand factor. So 220.55 is residential, 220.56 is for commercial. All right? You want to write that into your book, like you're going to have a question based on that, but you need to know what table is for commercial and what table is for household. All right, flipping over to page 14. You're going to run through an example problem that they have on page 14. So example 3, we're going to run through. You need to have it highlighted. Yours is going to be, you'll have problems based like this in the work that you have. So example 3, 1 wall-mounted oven and 1 counter-mounted cooking unit are to be installed in the kitchen. To reduce the cost of the electrical installation, both pieces of cooking equipment are to be connected to the same 240-volt single-phase circuit. One oven has a nameplate rating of 12.5 kilowatts, and the counter-mounted unit has a nameplate rating of 8 kilowatts. What is the demand load in amps for a single circuit to supply this cooking equipment? So what they're wanting to do is take both of these pieces of cooking equipment and feed it with essentially one wire coming from the panel. They'll split it up once they get to the two different things, but they want to feed this with one wire rather than running 2 home runs back to the panel, increasing costs, right? So seeing if they can do it. Solution, table 220.55 note 4. This is one of the more difficult things to do in this chapter. So please follow along in your NEC book while I'm going through this, because I use the notes at the bottom. All right. So 220.55 note 4. So looking in here, you look to the bottom of note 4, branch circuit load. It says, it shall be permissible to calculate the branch circuit load for one range in accordance with 220.55. The branch circuit load for one wall-mounted oven or counter-mounted cooking unit shall be the nameplate rating of the appliance. The branch circuit load for a counter-mounted cooking unit and not more than 2 wall-mounted units, all supplied from a single branch circuit and located in the same room, shall be calculated by adding the nameplate rating of the individual appliances and treating this total as equivalent to one range. So what does that note allow us to do? it says since we have, one load for a counter-mounted cooking unit and less than 2 wall-mounted units, I can combine those nameplate ratings and treat it as one. That's what this code, that note on that code is allowing us to do. So we go back and we look at our what are our nameplate ratings for those two pieces of equipment?
12.5 kilowatts and 8.0 kilowatts.
Added up, those are what?
20.5 kilowatts.
So this is two different ovens, but we are treating it as if it were one. Does that make sense? Two different cooking units treated as one. So now we have that total. The equivalent of the range is 20.5 kilowatts. Going to, now we're going to note 1. All right. So we're on note 4. Now I'm going to read through note 1 on that same page. Again, this is a harder part of this. Note, over 12 kilowatts through 27 kilowatts. Are we there?
Yeah.
We are right in the mix of that. So we're over 12, but we're under 27 of all the same rating. For ranges individually rated more than 12, but not more than 27, the maximum demand in column C shall be increased 5% for each additional kilowatt rating of a major fraction thereof by a rating of individual ranges that exceed 12 kilowatts. So what, going back to, one second. So it says for every kilowatt over 12, we have to increase it what?
By 5%.
5%. So now we have to take our total 20.5 and see how far we are over 12, right? So it leaves us with 8.5, right? Does it say? See where it says shall be increased 5% for each additional kilowatt or rating or major fraction thereof. See where it says major fraction thereof? What that means is you round. So we have 8.5 left over. What would that round to? So this rounds to 9. That's to me that's stupid confusing. That doesn't look like a 9. But it rounds to 9, and that's what we have to use, right? So now looking in our, it says that because 0.5 is a major fraction, the result is rounded to 9 kilowatts. Multiply this by 5%. So 9 times 5, what's 5% written as a decimal? And that gives me 0.45, right? 45. And then we, so that's an extra, what is 0.45 written as a percentage? 45%. So that's how much extra we have. So we have to take an extra 45%. So an extra, so to take the whole thing would be what percentage? 100%. We have to take an extra 45%. What's that total? 145%. We have to take the total. So now our note in 1 says column C shall be increased 5%. All right. So how many appliances do we have?
2.
But we're treating it as what?
3.
1. We have 2. I know this is confusing. We have 2 appliances, but we're treating it as 1 because of note 4. So we have 1 appliance, and then we go to column C. And what's our maximum demand?
27.
We have for 1 appliance in column C.
Should be
8.
Oh, yeah, I do.
So we get there. So now we have 8 times 145%. which should give us 11.6 kilowatts. So divide the total volt amperage by the circuit voltage to determine the branch circuit ampacity. So kilowatts is the same as what? Kilovolt amps. So what is this written in watts? What's 11.6 kilowatts written in watts?
11,600.
And watts can be written as volt amps, right? So those are the same. 11,600 volt amps. So now, if it's the first thing it's asking, or the question it's asking is for, is it's wanting amps. So how do we get amps out of volt amps? Divide by my voltage. What's my voltage?
240.
What's 11.6 divided by 240?
48.33.
I know that's a lot. That's why, that's why I'm gonna have y'all work on this stuff. I'm gonna give y'all a few more highlights, and then I'm like, that's why I want y'all to work on this in the off time. 260. Water heaters. First paragraph for water heaters is highlighted. As specified, NEC section 422.13, fixed storage water heaters having a storage capacity of 120 gallons or less shall have a branch circuit rating of not less than 125% of the nameplate rating of the water heater because it's considered a continuous load. All water heaters are considered, actually that's not true. Storage type water heaters are considered a continuous load. So what is a non-storage type water heater? Well, no,
That's the storage type of.
anything that has like a big
Oh, they
tank
had the water.
and it's storing the water and heating it up. Anybody have a tankless water heater? Nobody know. You don't know what tankless water heater is? Sometimes they have like a box on the outside of your house and water runs through it. So that, like you'll see on the outside of the house, you have a box like this, right? And you have cold water coming in here and hot on this side. We usually have gas or electric coming in right here, right? So this thing has tubes in it. They go back and forth, and go like this, and then eventually it comes out. This is gas or electric. This is putting heat in the bottom of this.
Them be like on garages and stuff like that.
Yes. So that puts heat in it. So whenever I turn my water on this side, water's flowing through this. It kicks on the circuit and tells the gas or electric start heating up. And as this is going through this, it's getting hotter and hotter the further it goes, right? So that's how kind of how a tankless water heater works. But this is a non-storage type, right? This would be tankless. But what they're talking about is like what I have in my house, like I have cold and hot. And like we use the hot water and say our water level is right here. And then we either have one or two elements that are electric, which then again, this will all be electric. This would be for electric dryers because gas, you won't have a lot of gas. You can have electricity running to my gas. I don't even have electricity running to my gas water heater. But if this was electric, I've got two elements, and all these is like a big coil of wire, big coil right there. And as this goes down, there's a little switch or float or something like that. This goes up, and then there's just a thermostat. Whenever the temperature of this goes down, because of cold water coming in and hot water going out, it kicks on these heaters, right? But I'm storing the water. Does that make sense? This is a storage type water heater. This is a tankless is not. So fixed storage water heaters having a storage capacity of 120 gallons or less. Most of your water heaters at your house are 40 to 50 gallons, right? 50 gallons, 50, 60 gallon water heater, that's like You walk into somebody's utility room, you're like, Jesus, we got a big water heater. Are rated at no less than 125% of the nameplate rating of the water heater. So if you have an electric storage type water heater, you have to say that the nameplate rating on this is, say this is 30 amps, right? What do I have to take that 30 amps at?
Here's 25.
125%. Why? Because these storage type water heaters are always considered a continuous load. Because say I took a shower, my wife took a shower, and somebody else in the house took a shower, and the water gets down to there, it's gonna take a while for that to heat that water back up, and it's being continuously used over the day, like throughout the day. All storage type water heaters of 120 gallons or less are considered continuous duty. So anytime you're doing a problem and it says water heater, you need to be thinking about multiplying by 125% or 0.8, depending on what your size. Page 15, electric heating loads. These are what you guys, unless you move up north, will never see. Page 15, right above the example 1, second to last sentence is highlighted. When space heating equipment utilizes electric resistance heating elements, protection for resistant heating elements shall not exceed 60 amps per NEC section 424 to 22B. Don't know what electric heating resistant elements are? Does anybody know? I have an answer for that. Well, I'll just go back. Everybody's used a toaster, right? Put down a toaster and you can see those wires in there getting red hot. That's electric resistance heating. So the same thing happens in like heaters. We don't use a lot of heaters down here and stuff, but when it does get cold, some people might plug something in and you see like those coils get red hot in there and then there's a fan behind them blowing. That's electric resistive heating. You just have resistive elements that you're passing current through, they get hot, and then you blow a fan over them, and it's a heater. Okay?
Those can be fueled with gas too, though. Sometimes.
Well, you can have a gas heater, but it's not going to have those wires in it.
Right.
And you're not going to run that in your house. Well, you could have a propane heater.
Yeah.
So it's-
my grandma got like an old propane heater, but like
Right.
where you got it's like it click like a.
You got a lighter?
Yeah, you got a
Yeah.
lighter. So that's why I'm saying.
So it's just, instead of having those wires, it's got a flame.
Right. Yeah.
I've got the example highlighted. What is the minimum conductor capacity for the following baseboard electric heaters? So not in Southeast Louisiana, but in other parts of the country. My wife's family is from Pennsylvania. They have electric baseboard heating. So they have these units that run alongside the baseboard that plug in. It's a lot bigger deal up there because it's a lot harder to get your house warm. And my wife's grandfather, I don't think he turns on his air conditioning up in Pennsylvania. He's got like, his air conditioner outside of his house is tiny, but he has to run a lot of heat in the winter. So not really what we have to mess with down here, but if you move somewhere else, you might have to calculate this stuff. But what is the minimum conductor capacity for the following baseboard electric heaters? 240 volt single phase, one is 1500 watts, one's 1000 watt, and two 500 watts. So all they did is add them all up for a total of 3500 volt amps. Divide that by the voltage that you're running to find your amperage. 3500 divided by 240. It's going to be 14.5 amps. And then, so water heaters and baseboard heat, are both what do? Continuous or non-continuous? Continuous. You're going to run that heat in your house for longer than 3 hours. So you have to take that 14.5 and multiply it by 1.25. What I would highly recommend when you guys are going through this, have a list, like write on a piece of paper, continuous duty, non-continuous duty. What are some continuous duty loads?
Heaters.
Heaters for your house, baseboard heat, water heater, storage type water heaters. Those are always going to be continuous duty loads. All right. Last couple highlights on page 16, air conditioning loads. 280, down at the bottom, last sentence in that paragraph is highlighted. If this breaker is not sufficient enough to hold the starting current of the motor, the rating is permitted to be increased, but cannot exceed 225%. Key in on that, cannot exceed 225% of the motor rated load current or the branch circuit selection current, whichever is greater. The example one is highlighted. Which size copper conductors are required for a branch circuit supplying an air conditioner with a nameplate rating of 45 amps, 480 volts, Jesus, that's a big air conditioner. That's a huge air conditioner, so 3-phase. So the solution is find 125% of the ampacity. So you have to multiply by 125, so 45 amps times 1.25 is 56.25 amps. All right, so before Wednesday, I want you guys to run through section 2 review. I want to see work done on page 17. If you have questions, that's fine. The other thing for this, like I want to see work being done. Does everybody know what the answers to these are? Pretty much. Does anybody not know? Everybody does know. Well, the answers to all these section reviews. Everybody flip to page 31. All section review answers are in the back of these chapters. If you didn't know that, that's fine. I'm not grading this. If you go through and just put the answers down and it has the work, like it has the work for section 2 review. You can write the work down, put the answer down. That's fine. I'll look at it. Whatever. You're going to fail the test. All right. I'm not checking this stuff. If you want to do that, like don't even bother doing that. It's not worth your time or my time. It would be better if you just left it blank. Okay. But it is going to be very advantageous for you guys to run through this and kind of struggle through some of these. And then you can check that stuff in the back for how to do it or your answers. Okay. So I'm going to go over this on Wednesday. And I would like questions. Even if you have to go and find like, hey, I see how they did it, but I don't understand how they did it. All right. So you're going to have to take this book home. Make sure you don't lose this. This is a school's copy for the most part. But by Wednesday, I want this page 17 done. Questions? All right, see you Wednesday. Don't get midterm grades yet. I don't know when they post that for y'all. They did. Can you check them yet? Midterm grades? I'm just curious. I don't know when the school puts those out. I mean, I know I showed everybody theirs.